There are actually third world countries that live longer than we do. And, you have to ask yourself, why are we doing so poorly? As a matter of fact, relative to the rest of the world, there was a recent publication on this. Relative to the rest of the world, the United States, since the 1950s, in lifespan has gone down. We continue to fall. Now the mean lifespan in the United States is around 76.4 years, whereas in Macau, it's approximately 87 years. Hong Kong, 85 years. Even Canada, I think it's about 83 years. Why are we doing so poorly here?
Hello?
So I always had a hope of getting to say this in real life one day in a way that mattered. What's up, Doc? But seriously, so two questions that are fun right now. How many times a week do you think about the Roman Empire?
I'm going to have to be honest and say 0.
Really?
Yes.
So if that's true, you're an anomaly, just so you know.
Are you kidding?
Yeah. So this is a trend that's like girls are asking their husbands how often they think of the Roman Empire, and it's like the answers you get are pretty funny. So then the other question, dude, what is the deal with this traffic? This is not the same place that I remember. I pulled in just onto Glades the other day. I felt like I was on the 5 in Southern California.
Yeah.
How much has this place grown since I've been down?
So, certainly during the pandemic, we had a huge influx of people, certainly coming from the Northeast. So it's very obvious how inundated we are. Now, of course, we are still off season. This isn't even season yet. So I'm imagining that when season hits, it's going to be a nightmare.
You having been here as long as you have, you feel like it's very different.
Yeah, well, you say very different, I can certainly appreciate the fact that it's more populated down here now, even off season, than it was pre-pandemic.
Mm-hmm. Okay, so keep in mind, this is not a talk. This is not a lecture. However, I do want to go through some high points of your CV just so my audience knows who you are.
Sure.
And I know that this is probably 30% of it, and you can tell me if I'm missing certain high points or if I'm getting something wrong.
Sure.
So you had your bachelor's degree at UPenn, 78, master's in physiology at Georgetown in 83, your MD at Georgetown in 86, and you were the assistant chief of emergency medicine at Walter Reed in DC. You have been assistant director of emergency medicine at Bethesda, also there. You have been or are currently president of the board of directors of the American Academy of Anti-Aging Medicine.
Well, I'm not president, but I'm on the board. I've been a consultant for the American Academy of Anti-Aging Medicine now for, close to 20 years.
Right. Okay. So, and then just going through this, so you have a pharmaceutical company. You are CMO at Rose Pharmaceuticals.
So that's all been sold and changed. So what ended up happening is we've changed company names multiple times, and we ended up merging with a group, a spin out of Harvard. Mm-hmm. And a couple of years ago, we ended up going public. And now we hope in 2024 to start human clinical trials. So the company is called Hillstream Biopharma.
Okay.
And so I don't play an active role, but I was the individual who brought the primary drug to the group from Harvard.
What's the drug?
Well, the drug was selenomycin. At the time, that was a drug that we found that targeted cancer stem cells. And for those out there that are familiar with the concept of stem cells, cancer stem cells are inherently resistant to our treatment, and they have the ability to self-renew and proliferate. So without getting too deep into the science of cancer, we do understand that one of the reasons for cancer resistance to treatment is the fact that we don't have drugs that target the cancer stem cells. And so what I brought was a drug that was shown to target cancer stem cells in the preclinical studies. And we merged with a company that was able to put this drug into a novel nanoparticle to really concentrate it, the drug where we wanted it to go. So we will see where this ends up.
It's a lipid capsule.
So yeah, but it is lipid, but it's much more complicated than a simple lipid capsule.
Okay. So you are Chief Science Officer and Director of R&D at Vitamax Vitamins.
So that's old. That I am no longer with that company.
You pioneered research with the University of Miami on inhibition of cancer growth through the inhibition of proton pump and monocarboxylate inhibitors, or monocarboxylate transporters.
Correct.
And you developed a drug cocktail for that, which last I saw was patent pending. Did you get the IP on that?
No, and here's the thing. As far as I've learned a lot about the significance of IP in medicine. So really what you want, if you're going to get funding, you want to get a composition patent as opposed to a methods patent. And so, my concept was definitely sound, and I'll explain very quickly. So many of the cancers, like you'll read all the time that people say cancer feeds on sugar. Mm-hmm. Well, cancer does feed on sugar, but it's not like it exclusively feeds on sugar. But many of the rapidly growing cancers will feed on glucose and process it through a process called glycolysis. Now, the end product of glycolysis is pyruvate. In the cancer cells, they convert pyruvate to lactic acid. Mm-hmm. So the cancer cells that are trying to rapidly generate energy, or ATP, are making a lot of lactic acid. They've got to get rid of their waste product, or their lactic acid. If they don't, they'll die of acidity. So what the cancer cells have become very good at doing is utilizing multiple pumps. And one of them, as you mentioned, was the monocarboxylate transporter. But they develop pumps to get rid of their acid. And when they pump the acid out of their cell, not only do they protect themselves from dying of acidosis, but outside the cell now becomes very acidic. Mm-hmm. We call that the tumor microenvironment. The more acidic the tumor microenvironment, the more it promotes its own proliferation and metastatic spread. So what I did is I put together a cocktail that I'm still using in patients that block the cancer's ability to pump out its own acid. Nice idea, but it's not going to draw a lot of money for funding, because in order to do that, we're coming back to the concept of composition patent. So we want a new molecule. Mm-hmm. Even if you have an existing molecule that works well, but there's no IP there, nobody is from a financial research. Nobody's going to fund it. Yeah. So it's not that the cocktail certainly didn't go anywhere, and I understand.
But the good news for patients is that these drugs exist, and you can already use them in an off-label basis, right?
Correct.
So, okay, so you also developed an oral appetite suppressant drug.
Yeah. So we ended up not raising the money and going anywhere. What I did, there's a hormone called cholecystokinin, abbreviated CCK, and cholecystokinin will inhibit appetite, and it will get released in response to eating a fatty meal, mostly fatty meal, but also protein. Mm-hmm. And as a matter of fact, one of the problems is with aging individuals in their 80s and 90s, we often see them start to waste away or get cachectic, even if they don't have cancer. And what we've seen in older individuals is an increased secretion of CCK, or cholecystokinin. So when I was looking at developing a diet drug, I thought, well, that'd be very interesting if we can either develop a similar molecule that binds to the CCK receptors. But what I ended up doing is figuring out how to just take CCK and stop it from being degraded by intestinal enzymes. So the problem is CCK orally doesn't work, because if you give it to them, the intestinal enzymes will degrade it and it won't get there. So I figured out how to prevent the breakdown and make oral CCK now work. And we did a small study. It was approximately 50 individuals, and we had tremendous weight loss. Now, the thing is, the IP, again, the composition patent was not very strong.
Mm-hmm.
And so we ended up abandoning it because even though it worked very well.
But the delivery method was.
Yeah.
So
yeah, go ahead.
So can you drop your mic down just a hair, it's a little above you?
Oops.
So.
Oh, maybe here?
I would think, though, that might be analogous to what OxyContin was. That wasn't a new compound. It was just an extended release oxycodone.
Mm-hmm.
And so Purdue had the IP on that.
Sure.
And that was all about the extended release, right?
Yeah.
How does that work?
Well, I honestly, so I not only hired a patent attorney, but this patent attorney is also an MD, and we worked on it together. Now, I can't tell you the intricacies of why it wasn't strong enough, but I deferred to him because that's what he did for a living. And we were simply not able to raise money. It didn't generate as much interest as we hoped. Yeah.
That's, given the demand for, like semaglutide and some of these other peptide compounds, it's sort of surprising to me that there wasn't more interest for that.
Timing is everything. And I think had I, now of course the peptide semaglutide, tirzepatide, they're so hot right now. But I think if I were to reintroduce it in this time period, the response may have been, much different.
Okay. So first and foremost, to me, in 2014, my mother was diagnosed with glioblastoma, which they don't stage brain cancers, they grade them. And glioblastoma is grade 4. It's as aggressive and as poor prognosis of a cancer that a person can have. My understanding, other than maybe pancreatic cancer, but it's close, or non-small cell lung cancer, right? And we found out that my mother was diagnosed with that after she had brain surgery at Cleveland Clinic. The surgeon walked out and said, this is what I see. And I had done enough homework when she started showing symptoms to know, if you're going to have brain cancer, this is the one that you don't want to have. So we were devastated by that. And the conversation that we had at Cleveland Clinic was that the standard of care is an oral chemotherapy drug and targeted brain radiation therapy, right? And so the prognosis with that standard of care was that the median survival time for these patients was 12 to 14 months. And they explained that through the process of the radiation, that she would have cognitive deficits, she would lose her hair, and it would impact her quality of life significantly. And it just felt very much to me like I was being told, you're going to pay for your mom to go through this treatment regime. It's not going to work. It's going to worsen her quality of life, and then she's going to die. And that wasn't something that made sense to me or that I was able to, frankly, just immediately accept. So a dear friend of mine, Kathy Gornick, who I just inherently trust, I'd had long conversations with her. I know her husband, Jim, had gone through cancer treatment and ultimately passed away. But what Kathy kept reiterating to me, and I can tell you the exact words that she used, was that you need to go see this doctor, Mark Rosenberg. Yes, Jim passed away, but there's no way for me to express to you what this doctor means to me. I really feel that for what he did for me, I have a debt to him that I can't repay. It's not possible. So we explored other options with Mom first. We were actually in Tijuana and were feeling pessimistic about the level of care that we were getting there. And this is before Keytruda and Opdivo became high-selling drugs. And we were trying to find other avenues to that sort of immunotherapy course because it offered maybe a better standard of living and also maybe a little more hope. And through Kathy's persuasion, we drove across the border from Tijuana to San Diego, and we flew straight to Boca Raton to you. And we lived here for that summer, and you treated my mother, and yes, my mother did ultimately pass away, but I feel that, the median survival time for the disease that she had is 12 to 14 months. My mother lived 2 years. And on top of that, a year into it, my mother was able to celebrate at my wedding and dance more than I did. And some of the best memories that I have of my mom in my life were times when she was going through the course of that disease and through the course of that treatment. And so I think I sort of have arrived with you at the same place Kathy did, which is to say nothing of the fact that it would be an exaggeration to say that you've saved my life over the last couple of years, but it wouldn't be an exaggeration to say that having you as an advocate, a person who trusts and listens to me, has at minimum preserved my sanity. So just on a personal level, it's very important to me to have this conversation for people who I'm connected with, to know who you are and the role that you've played in my life. So, and the thing that I appreciate about you is you're not someone who is openly hostile to institutional medicine. If the standard of care works for cancer patients, you tell them that that's what they should pursue. And you have a lot of depth when it comes to the actual science. But you're also someone who has a lot of breadth and a lot of depth as an independent thinker, and you're patient-centered, and your mission really is to help people. And I just, on top of your cancer practice, you're someone who is always on, I feel like there's always this huge gap between science and the practice of medicine, right? And I've always felt like you're making your best effort to stay on the cutting edge of what the science says about whatever you're treating a patient for. And just to have you in my life has been a huge lifeline, as a person to me.
Thank you, Thad.
So just to set this up a little bit more, I listened to a decade ago, I listened to a cancer talk that you gave, and I think the premise of it was how fundamentally unsound animal models of cancer are. And you made a remark in the course of that lecture to the effect of that we as an industry have forgotten how to think. Is this ringing a bell for you?
Sure.
And just that sentence of "we have forgotten how to think" is something that sort of just stuck in my brain and has stayed with me for the last decade. And there's been a lot of context for me that's built up around that. And I think you and I were talking the other day. In economics, I have an economics degree. There's a phenomenon known as crowd out, which is, and probably the most obvious example of crowd out is this: someone plans to save for retirement. They plan for retirement. They save a certain amount. Then the Social Security program is introduced. They know that they're going to have that income in retirement, and so people are dynamic. They respond to incentives, and they say, "Well, I know I'm going to get that. Maybe I save a little bit less for retirement." I see this phenomenon of crowd out in a lot of other things other than money. And I really see it in healthcare in the sense of, like you said, people have forgotten how to think. They've sort of, it feels like people have farmed out their own cognition to the institutions. And to me, that's really tragic and really dangerous, because it's like, okay, so you go to a doctor, the doctor has a guidebook, they have the standard of care, they're going to practice medicine in a way that if they get sued, they can say, "I followed the standard of care, this is entirely defensible," right? And then the institution that they're employed by also doesn't want to get sued. And so they're referring to guidelines. Okay, who writes the guidelines and who pays for the institution that writes the guidelines? And it's just this, all the way down the line, people are passing the buck, because there's all these other incentive structures at play other than what does the science say and how do I help this patient? And I've always been struck by, you have this long set of credentials from your work, but also from the institutions where you've been educated. And also, you're really a scientist as well as a doctor. And yet, you haven't decided to go into institutional medicine. You run a practice where you practice anti-aging medicine. You help people, like me, who are just sort of out of the box on an individual basis, but you also sort of operate this practice for people who have cancer, who the prognosis from the standard of care doesn't offer much, right? And it's an interesting juxtaposition to me of the way you've decided to practice medicine against your background and your credentials. So I was hoping maybe you can explain a little bit about how you arrived there.
Sure. So my board certification and formal training was emergency medicine. And in the United States, we are great at acute care. We're great at emergency medicine. And I am thankful for my training in emergency medicine. And I know that a lot of what I did really worked. What happened was approximately 20 years ago, my mom walked into the emergency department when I was working, and I diagnosed her with metastatic non-small cell lung cancer to liver, spleen, bilateral adrenal glands, and left hip. Now, at the time, I didn't know much about treating cancer. I was an emergency medicine specialist. We took my mom up to Philadelphia, and that's where they explained that chemotherapy for most advanced stage solid tumors extended survival by about 2 months over doing supportive care. And that blew me out of the water. And so really that's where my journey began. So I started reading whatever literature I could find on treating cancer worldwide, just on the internet. And I presented my mom with everything I could find. And my mom was told that with chemotherapy, she may live 6 months. With no chemotherapy, she may live 4 months. So my mom, of course, knowing that data, she refused chemotherapy. She said she would do IV vitamin C, intravenous vitamin C, which I didn't know anything about, but we did it. And my mom lived 11 months. And I'd say 10 of those 11 months were good quality. But that's where my research began. And from then on, not only, of course, did I constantly read the literature as I do today, but that's when I did some in vitro studies, and that's when I ended up bringing a drug to the group from Harvard. But, I've learned a lot over the years about cancer. And one of the things that I've learned is we haven't learned very much about cancer. And so I'll often say this to patients. 1,000 years ago, what would we do if we found someone with cancer? Well, we would cut it out. And if we cut it out on time, you won, meaning the patient was free of cancer. And if you didn't, then of course, they would eventually succumb to the disease. Fast forward to 2023. Not a lot has changed. If you cut the cancer out in time before it has spread, then the patient will be cured of their cancer. If not, what we're doing is buying time. And unfortunately, the time we're buying is still small. We've improved in very small increments. And I'll quote a publication that came out in the Journal of Clinical Oncology about 6 months ago. And what they did is they looked at every new drug that has come out for cancer treatment over the past 2 decades. And the primary objective was to determine what was the improvement in overall survival with each of these drugs. And the answer was 2.8 months. So that's what these drugs are doing. Now, what we're all doing in the research of cancer is trying to find new targets. Now, We've had many years to learn that we're treating cancer. A great analogy is the children's game Whack-A-Mole. So with Whack-A-Mole, you whack this one mole and another one pops up and another one pops up. And so a lot of our research has been targeting gene mutations. And we know when we target one gene mutation, we will buy a little time. But it's only a matter of time before another mole pops up, and another mole, and another mole, and another mole. Now, you may say, well, if all of these targeted therapies that we've been developing have yielded, 2.8 months increased survival, why are we doing that? It pays the bills. Mm-hmm. So the bottom line is every time you come out with a new drug, and we're not fooling ourselves. We, as scientists, we know it's not going to cure the cancer. But if you can improve survival by 6 weeks or 8 weeks, and you can show a statistical significance, you may have $1 billion drug on your hands. So, now I also get the concept that, okay, if we can buy another 2 months here, and then with this drug we buy another 2 months. And, eventually, maybe 20 years from now, we can get 20 years out of it. Mm-hmm. But so far, the cumulative increase in survival, in my opinion, is absolutely unacceptable. And, I think the whole paradigm, the whole thinking, the whole approach to treating cancer has to change if we want to make some significant improvements. Now, I just gave myself a segue into something else. And please allow me to expound upon this. You and I have spoken before about how is the United States doing relative to the rest of the world with regards to lifespan. Well, the latest data shows that the United States is number 51 in lifespan. I believe Cuba is 46. Costa Rica, Nicoya, Costa Rica is a blue zone, so they certainly live a whole lot longer. But there are actually third world countries that live longer than we do. And, you have to ask yourself, why are we doing so poorly? As a matter of fact, relative to the rest of the world, there was a recent publication on this. Relative to the rest of the world, the United States, since the 1950s, in lifespan has gone down. We continue to fall. Now the mean lifespan in the United States is around 76.4 years, whereas in Macau, it's approximately 87 years. Hong Kong, 85 years. Even Canada, I think it's about 83 years. Why are we doing so poorly here? Well, I'm going to reflect back on something I said earlier, that we are really good at acute care. So we're really good when someone has an emergency, like my training, emergency medicine. So we're really good at taking care of crisis. But are we good at managing disease? Are we good at preventing disease? And the answer is no. And we've become worse and worse, which would explain why our lifespan relative to the other countries is so poor. As a matter of fact, without naming names, one of the Johns Hopkins scientists was also looking at the same issue and remarking on the fact that, this is actually what he said. He said, in the United States, our lifespan relative to other countries is really poor. And his question was, in these other countries that don't have the technology that we do in the United States, many of them are living longer. So his question was, what are they doing in these other countries to improve their lifespan? And I think he's looked at it wrong. The question is, what are we doing in this country to reduce our lifespan? And again, everything comes down, in my opinion, to money, power, and greed. And if you look at what's going on in the blue zones, Sardinia, Italy, Loma Linda, California, Nicoya, Costa Rica, the Japanese district of Okinawa, what are they doing? Well, it's all very simple. They don't have this incredible technology, but they live in these large social groups. So they have amazing social support. Now our support here is we text very well, and we have all the social media. That's not the same as living with a group of 50 people that you can share your life experiences with. These people work all day physically. They grow their own food. They are eating food that is mostly plant-based and not loaded with pesticides. They're not eating all this refined packaged food that we have here. So they're getting exercise throughout the day. They're eating healthy, mostly plant-based foods, and they don't have the stresses that we do in our world, and they have great social support. Those are all the underpinnings of what they're doing to live much longer. So, we can segue into, okay, what are the different modalities? What are we researching? What are the scientists researching to help people live longer? And I can get into all those different modalities. But one of the simple facts that I would state is, maybe if we simply lived like they do in these blue zones, without introducing any of these new drugs or technology, or David Sinclair's latest research on loss of epigenetic information, if we simply lived a simple life where we didn't contaminate our foods, we weren't exposing ourselves to millions and millions of toxins per day, and we had social groups, and we exercised, wow, our mean lifespan would skyrocket. But I know in this country, we are not going to do that. We are looking for that magic technology to bring us where we want. I'm honestly not very hopeful. If what's been going on for the past 70 plus years is telling us where we're headed, I'm not really optimistic.
I want to expand on that just a little bit with a couple anecdotes. And maybe you know this already. You're familiar with the rat park study, mm-hmm. where they took the rats that were in an enriched environment versus an environment that was very sparse and very inconsistent with the nature of them as biological creatures, right? And they gave both of these groups the option of a water source that was just water or a water source that had cocaine in it, right? The ones that were in Rat Park, who were in this enriched environment, never chose the cocaine. The ones that were miserable started hitting the cocaine button over and over and over and over again until they died. And I think that's a pretty good analog for who we are and also for where we are right now. You're talking about this desire to find a technology or an innovation that will fix us. And I completely agree, but at the same time, what you see right now is we do live in an environment that is very artificial for us. We're eating food that's not consistent with our biology, and we're socialized in a way that's not consistent with our DNA and our nature as human beings either. And what do you have at the same time? You have an opioid epidemic that's worse than we've ever faced in this country. To me, it's a perfect analog, and it reinforces exactly what you're saying. And I'll go a step further about the medical industrial complex. And I know that's a very politically loaded term. Maybe I shouldn't use it. But if you look at, and this is just me, I'm not a doctor. I'm just a guy who tries to pay attention. But if you look at the models of disease that have become prevalent over the past 30 years, it seems very much to me like a drug is introduced that has an impact on the symptoms of a given disease, and suddenly the conventional thinking on the model of disease is built around the mechanism of that drug. When MAOI inhibitors were the popular drug for any type of mental illness, the conversation that we had was that mental illness was a product of too much monoamine oxidase. Whenever SSRIs became really, really common in the 1990s, the conversation became, depression and anxiety and these mental illnesses are a product of a serotonin imbalance. We know that both of those things aren't true. And I'll keep going. We thought that ADHD was a dopamine deficiency. We know it's not. We know that in an ADHD brain, there are structural differences in the gray matter of a person's brain that are observable. That's not a chemical thing. That's a structural thing. But it just so happens that the drugs that we use to treat those symptoms increase our dopamine levels, right? Keep going. Alzheimer's, the amyloid plaque hypothesis, how many Alzheimer's drugs have we introduced around that amyloid plaque hypothesis that have had really no significant impact on the severity and duration of Alzheimer's disease?
In addition, and I apologize for interrupting, but you may know that there are plenty of individuals who have a significant amount of amyloid beta plaque who have no symptoms.
Right.
Yeah.
So that brings me to a couple things that are a little controversial, which is one thing that I've heard a lot is that Alzheimer's is sort of like type 3 diabetes. It's diabetes of the brain. I don't know enough about the chemistry of how that works, but it appeals to my sensibilities. And the other thing that I hear too is that the lipid hypothesis has really been challenged in recent decades. You know, these cholesterol drugs are some of the top selling drugs in the world, but it's my understanding there's no data that demonstrates that elevated cholesterol contributes to heart disease in the presence of adequate insulin sensitivity. Yeah. Usually those things go together. You're insulin insensitive, and then you have too much HDL, right? But it's to me, it's a question of how much of these things are correlation and how much of these things are causation. Sure. Right. Sure. So can you talk a little bit about what you think appropriate disease model for Alzheimer's disease is, and then after that, what do you think about the lipid hypothesis?
You know, as far as an appropriate disease model for Alzheimer's, I'm sure you know, it's still controversial to this day. I mean, I was literally looking at the literature a week ago, and there are folks on the side of amyloid beta being the culprit still. And as a matter of fact, one of the latest drugs that recently got approved, it got approved because it slowed down the deterioration. It decreased amyloid beta plaque, and it statistically significantly slowed deterioration. Didn't reverse it, didn't improve it. It slowed the deterioration.
How is that the metric? That has nothing to do with how the disease manifests itself, right?
No argument there. So I think, is it possible that amyloid beta plays a role? It may play a role, but in my opinion, it is not the primary causative factor. And it may be somewhat causative, but maybe more so a result of the disease process. And so I think, in my opinion, we need to look elsewhere. For example, there's another drug in trials called TB006, and that the company's True Binding. And that's a galectin-3 inhibitor. It's a monoclonal antibody against galectin-3. I think looking more at the oxidative stress, looking more at the microglia, which are basically the immune system of the brain, I think there's more, there's potentially more positive findings. Well, in preclinical, we have seen some positive findings, but I think that's more of an area that we need to put more of our research in. But do I feel like the data is clear enough for me to really explain the disease model? And the answer is no. And one of the reasons, again, we go down the path that we think is going to make us financially in a better situation.
It does seem to you like the tail is wagging the dog.
Without question. And I think how long, how many more years are we going to spend still just saying amyloid beta plaque is the problem and we just need to come up with a better drug? So I don't have the answer. And I apologize. You were talking about the lipid hypothesis specifically for
heart disease.
For heart disease. So very interesting. I'm going to reflect back when I was many, many years ago when I was in medical school, there was not a disease called, when I say a disease called, I'm talking about ICD, ICD-9, ICD-10. So there was no diagnosis code when I was growing up, when I was in medical school, for hyperlipidemia, right? Hyperlipidemia, also known as elevated lipids, was simply a risk factor for cardiovascular disease, like it is today, right? It's considered a risk factor. But then we developed a drug, and we developed a class of drugs called statins. Now, when you develop a drug in this country, it's got to treat a disease, right? That's how you can get reimbursed. So what did we do is we developed a disease called hyperlipidemia. So hyperlipidemia became a disease unto itself. So now we got a drug to fit the disease. This is where we
a disease to fit the drug.
We have, I apologize, yeah. We have a disease to fit the drug. We got a drug, we know this is a great drug. It does what we want, so we've got to find a disease to fit it. And you're right.
It seems like we do that over and over again.
We do.
No, and I understand, my background is in economics, and I understand that people respond to incentives, and people are not going to do the research if they can't get the IP on a drug because it takes $1 billion or more to bring a drug to market, and it's just not worth it. As rational human being, as rational self-interested companies, it's not worth it. That said, I don't understand how we fix it.
So people have called me a pessimist, and I don't mean to be a pessimist, but humans have been run by greed, power, money since, I believe, prehistoric time. Obviously, I don't have data to say what went on in prehistoric times, but certainly in recorded history, nations, individuals have been run by power and greed. And when I say I'm pessimistic, I don't see the paradigm changing because, as you talked about incentive, there's got to be an incentive to change. And what the people in power look at as incentive is being rewarded with money. That's typically it. So although, you and I can pontificate on, what we'd like to see change and wouldn't the world be better if it were this way, and it's all nice. I don't see it happening. I just don't.
But I do think what you're seeing is the internet and podcasts and some of this independently funded literature that's coming out is reaching people in a way that it's never been able to before. And I think you're seeing a lot of individuals sort of wake up to this reality. And so there's a question of how do you change the system, but I think there's another question of what can individuals do to stave off disease, and what can individual practitioners like yourself do to help these people who are sort of these independent thinkers.
Let me interject something. You bring up a good point because I've had patients that have argued with me and said exactly what you said. The internet is good and bad, of course, but it's allowed the word to spread more. Social media has allowed the word to spread more. And there are so many more people who see what's going on, so many more individuals like you and I that see what's going on. And so their point to me was, because that minority is growing and growing and growing, eventually they'll be able to make a change. Now, my response to that was, however, there are small groups that have the power. There are small groups that have the money, and they are still dictating what's going on. So I appreciate the fact that the minority, which are the people who really didn't know what's going on, they're growing and growing. But are they going to have the tools to be able to impact what is happening, to dictate what is happening? And I think it's going to, you bring up a good point. What can the individual do? And I'm going to tell you one of the things that I typically when I have a new patient with cancer that comes to me and they say, we want to extend survival as much as we can. And I tell them this, you need to be your own quarterback. Even though your oncologist wants you to do well, he only knows what he knows, and he's going to follow the rule book. Now, we are all aware that cancer is a unique disease to every individual. And the reason it's a unique disease is because, kind of like playing chess, there is going to be unique responses by your own body. Every time you try to kill cancer, there's going to be a response. And the response is going to be unique in every individual. Now, having said that, the oncologist is going to treat every pancreatic cancer patient with exactly the same regimen. Every non-small cell lung cancer, every glioblastoma, everybody's going to get the same treatment. Now, if every cancer is unique, and it's genetically unique and epigenetically unique, and it's a dynamic disease, if every cancer is going to respond dynamically, uniquely, how can everybody get the same treatment? That doesn't make any sense, of course. But it also would be way too costly to treat every individual with cancer uniquely. It doesn't make any figurative or literal sense. I get it. So I tell every patient, you and the family with them, you need to be your own quarterback. Gather all the information you can. And I tell them, don't put all your blind faith in your oncologist or even me or anybody. You've got to become educated. You've got to read the literature as best you can. And you have to be the quarterback and help guide your doctors on what you want done.
And you have to balance not only what the science says, what the literature says, but you have to balance that in context with your own values on how you want the progression of the rest of your life to go.
Absolutely.
Right? There's a set of trade-offs there, but it seems like we are making progress on some of this, with at least as second and third line care on cancer. You do see these companies that are doing genome sequencing of tumors and looking at, at least what chemotherapy drugs may or may not be effective for this type of cancer, or even looking at, double, triple negative breast cancer and what drugs may or may not be effective in those sorts of diseases. Do you disagree with that? Do you feel like we're making progress in that way? Or
again, you're talking about genomic evaluation, and I actually have. It's been a while since I've spoken to the scientists, but there's an MD, PhD friend of mine who spent 15 years at the National Cancer Institute researching drugs based on genetic sequencing. And he quit because he said, I'm playing whack-a-mole and I'm tired of playing whack-a-mole.
No kidding.
Now, having said that, have we made some headway coming out with these targeted drugs? We've made some headway, but it's not nearly enough. And I'll tell you one of the projects that I'm working on, and I'm going to give a little basic science explanation to answer a basic question. So how does cancer go from being a primary disease to a systemic disease? So let's say a woman has a breast tumor. How does it go from being localized in the breast, to where we can cure it, to being metastatic, meaning it's spread to other parts of the body? And the old paradigm, and a lot of oncologists are not aware of it because this is the science of oncology. Many oncologists will say it's a late process, but what happens is later on in the more advanced disease, cells break off from their primary location and eventually find their way into circulation and spread. Well, here's what we have found out. We're now finding out that very early, it's an early process. It's not a late process. So, for example, in one study, they looked at patients with colorectal cancer who had metastasized to the liver. And they wanted to find out, when did those cells actually get to the liver? So they did studies to look at the lineage of those cells in the liver. And they found out that 80% of the cells in the liver got there before the primary colon lesion was as big as a poppy seed.
Wow.
So it's an early process. Now
You just don't see the manifestation of it.
That's
until
exactly
later.
right. And you raise a good point. We don't see the manifestation because a 1 millimeter cancer lesion, represents at least 1 million cells. Wow. Now, we don't even comment on a 1 millimeter lesion. When a radiologist is looking at your scan, 1 millimeter is a dot. We generally don't even comment, but that represents 1 million cancer cells. Now, what we've also found out is that it's not the individual cancer cells that break off in the primary location that's a problem, because they end up getting killed in circulation by either the hydrostatic forces or the immune system. But it turns out that there are very unique clusters of cells that will leave the primary location. And these clusters are both genetically and epigenetically unique and predetermined to leave as a cluster. And I call it a neighborhood because they don't just leave as a group of cancer cells. They leave with being protected by a group of neutrophils to physically protect it. They may leave with some endothelial cells to help them develop blood vessels. They may leave with some cancer-associated adipocytes to nourish them. So this neighborhood leaves.
They're bringing an ecosystem.
They are bringing their own ecosystem, and they are well protected, and we don't know how to kill them. And they eventually enter circulation, and then they just start spreading around the body. And so what I ended up doing is a few years ago, hypothesizing that what if we can do this? What if we can develop an extracorporeal circuit where your blood leaves your body and goes through a filtration device where we can, as often as needed, eliminate every single cluster, so we bring it to zero and keep it as zero by filtering it as often as needed? Could we then convert a systemic disease back into a focal disease? So that was my hypothesis. So we actually we have a filter, and we did 2 in vitro studies at University of Michigan, but I was not happy with our methodology. And so what we ended up doing is we are going to remake our filter, and we are now speaking with a veterinary oncologist. I won't say which university because they haven't signed off on it yet, but here is our project. We want to take hemangiosarcoma, which is probably the most aggressive cancer in dogs. And the reason I want to take that is because they probably, when a dog is diagnosed with hemangiosarcoma, they probably have another maybe 6 months. And so what we want to show is that we're going to hook them up to our filter. And what we want to do is we want to quantify the number of clusters before we start. And we want to quantify what are the components of those clusters so we can identify how many endothelial cells, how many tumor cells, to really identify which clusters seem to be the biggest problem. And then we run them through the filter as often as needed until we can quantify and say, we're down to 0 clusters. And what I plan on showing is that if we keep it as close to 0 as possible, we can keep these animals alive much longer and with a better quality of life.
I know that circulating tumor markers have been something that you've always focused on. One question I have about what you're telling me right now is if early on in the origins of the original tumor, these things have already metastasized more than we see. Isn't, by the time you've figured it out and then you're using that filter, isn't it too late?
Well, no. So that's a good point. And people ask me, would the utility of this filter only be for advanced disease? And the answer is the utility would be all from early to late stage. So let me explain. For many patients who we think they have early disease, and we say that based on the imaging, and we do a biopsy. Let's say it's in the breast, and we did a lymph node dissection, axillary or sentinel lymph node biopsy, the axilla, and there's nothing there. And the tumor is less than 2 centimeters. We say you have stage 1 breast cancer. Well, there are a percentage of those patients who already have circulating clusters. Now, we don't know that because that's not standard of care. We don't measure that. We don't check that. I can promise you, this is published. There are a group of those patients with the oncologists say, this is a slam dunk. We're just going to do a lumpectomy, and they may or may not give you adjuvant chemotherapy. In this case, what I'm talking about, assuming the cancer is an estrogen receptor positive breast cancer, and it's stage 1, they're just going to put that patient, if they're postmenopausal, they'll put them on an aromatase inhibitor. If they're premenopausal, they'll get on tamoxifen. Mm-hmm. They will recommend radiation, and they'll say, you're cured. Mm-hmm. But are they cured? Well, there's a subset that won't be. So we could start using this screening to know who are the high-risk patients. Now, even if you're stage 1, if you've got circulating clusters, you've got a very high chance of not only recurrence, but metastatic seeding. And so we need to be doing, and if we find what we call an early stage cancer with circulating clusters, we've got to bring that to 0.
Do you think this is a proxy for the 5-year, I don't want to say metric, but the 5-year categorization of once you get past the 5 years, your survival tends to be better? Is that because you think the patients that get past it are usually the ones who didn't have those high levels of circulating tumor clusters?
Absolutely.
Are they proxies for the same thing?
Absolutely. But I want to tell you this also. Now what we are seeing is that patients with hormone receptor positive cancers, meaning estrogen receptor positive cancer, they still have recurrences at 10 years out, 15 years out, 20 years out. Now, and we're all surprised. It's well documented in the literature, and I see patients all the time. Oncologists see patients who they were cured. They were 10 years out, and it so-called came back. Well, it's only our ignorance because it never left. And these are patients that we can start picking up and know early on who is going to be recurring. So,
and there are labs for this right now.
Well, so there is a lab test to look for individual circulating tumor cells, but there is no test out there. And this is not rocket science, and of course this can be done. But we need to be looking for clusters from the beginning. And it is not part of standard of care. But this is something that needs to be done. And again, so if you were to ask an oncologist, okay, so let's say you found clusters. Well, the guidelines don't tell us to do anything with those clusters. They won't do anything. If there is not disease that they can see on an imaging study, you will not be treated. So we've got to change our paradigm. We've got to say, okay, we have a test to look for these clusters, and now we have a treatment for these clusters.
When you present this at conferences, how are you received?
Well, the thing is, I'm presenting them at alternative conferences because those are the only people who even care to listen to this. Because, when you look at what is presented at most of these academic conferences, it all comes from pharmaceutical research. What we want to do is we want to make another drug that is going to, improve our treatment of cancer. So, I think that, again, we talked about the whole paradigm needs to be changed. I feel like we need to get really good young thinkers that are maybe 18 to 25 years old and are not educated in oncology, to be honest. We need some new thinking. We need thinking that is not biased by the current paradigm.
Where the parameters are already defined, the premises are already defined.
Absolutely.
So I know, it's easy to go down the cancer rabbit hole with you because I know you've treated a lot of cancer patients, and this is something you've applied your mind to a lot over the years, even from my own mom. But in my mind, you are someone who was on the curve early on a lot of the anti-aging conversations that are happening right now. Yeah, the people who have become these pop cultural figures like David Sinclair and Andrew Huberman, and even to some extent Walter Longo, only recently, you were into this stuff 15, 20 years ago. What are... And the same thing is true for cancer treatment. You and I were having conversations about immunotherapy and how transformative this is going to be before Opdivo and Keytruda became commonly used drugs. What are the things that people are missing now? So we've already sort of covered, we're living this artificial environment that's not consistent with our needs and our nature. But what are the practical steps that an individual can take that you would most highly recommend to stave off disease and to expand their health span?
So yeah, that's a loaded question, and perhaps the first thing I'm going to say is not practical for many people. But if you're living in a country that predisposes you to dying younger, and of course you will know why. They're like, for example, poor African nations. We know many of those people are dying of infectious diseases because they don't have the appropriate antivirals, antibiotics, antifungals. And so we get it. If you're in the United States, well, the data speaks for itself. And we know that there are many contributors to short lifespan, such as being overweight or obese. 70% of the population is at least overweight. 40% in this country is defined as obese. Now, if you would
That's based on BMI data, which is questionable.
That's correct. And I'm not going to argue that is questionable as well, but I think if you apply it to the bulk, it probably has an application. Now, obviously, BMI is worthless for a bodybuilder, but I think as a general rule, it applies to this population. Now, if we were to take all these overweight and obese individuals and put them in Nicoya, Costa Rica, I'm going to promise you that most of those obese individuals wouldn't be obese anymore. So when you ask me, what would I tell patients, what would I tell individuals in this country?
Move to Costa Rica.
Move, or move to the Japanese district of Okinawa. So the easiest way, which is not practical, is to move to a place where people are living a life that predisposes them to being healthier and living longer. Because it's hard in this country. It really is. And I get it. Our technology is great and we have the best of acute care medicine, but that does not translate to healthy, long lives at all. And I honestly don't see it ever translating. So the first thing I'd say is if you can move. Now, having said that, if you can't move, again, it comes down to the basics. Again, we could get into all the different modalities that are looking. So, for example, tomorrow I will be overseeing therapeutic plasma exchange. And that's a segue. If you're okay, I'll talk a little bit about.
Yeah, let's go.
Okay. So every organism on this planet.
Just making sure that okay.
Okay, yeah. Every organism on this planet, except perhaps one type of jellyfish, as we know, every organism is programmed to age and die. And so, of course, the obvious question is, where's that programming located? Well, there are interesting thoughts. Certainly, David Sinclair's latest thought is that we're losing the epigenetic information, and certainly, that loss of epigenetic information is considered one of the hallmarks of aging. Is it the only one? Is it just a contributor? I don't know. But what we do also know is that many of the cells that are floating in our plasma, the liquid portion of our blood, are carrying bad information. And when I say bad information, this is cumulative bad information. So, for example, there are circulating immune complexes. So you have your immune cells that will respond to pathogens, and that occurs from a baby up until the time you die. Now, many of those complexes, meaning the immune cells binding to these pathogens, they don't go away, and they circulate and accumulate. So we know that as you age, you are just loaded with these circulating immune complexes. We know that the proteins that are produced are changing as we age, and we're not producing the benevolent proteins that we used to. They're accumulating. Senescent cells, just for the audience, people call them zombie cells. Every cell in our body has a certain number of cells, a certain number of cell divisions. We call that the Hayflick limit because in 1961, Dr. Hayflick took different cells from the body and grew them in a culture medium and determined that they all have a certain number of cell divisions, typically somewhere between 25 and 75 cell divisions, and they're done. So when a cell is done dividing, it has two options. It can either die, or worse than that, it doesn't die, and it becomes what's called a senescent cell, where it basically sits and festers and releases inflammatory cytokines that promotes the senescent associated secretory phenotype, and it becomes a vicious cycle. They release more inflammatory cytokines. So all these and toxins, all these bad components are accumulating in the bloodstream. Not to mention exosomes. So exosomes are little snippets of RNA, DNA, protein that will, it's the way the cells communicate with each other. Now it's estimated that there are at least 1.8 billion exosomes per milliliter of blood. Well, I can promise you, me at my age of 63, I've got exosomes that aren't saying the kind words that my exosomes were saying when I was 20 years old. So we have all these toxic substances floating in our bloodstream. So there have been some interesting studies that were done at Berkeley. And what they did, they first started out with mouse studies. And they hooked up the circulation of a young mouse to an old mouse. And what happened was the old mouse got younger. Now, the young mouse didn't do any better, certainly. So that was very interesting. And then that led to the concept of what's called therapeutic plasma exchange. So what they did with 8 individuals is they would monthly bleed off a full plasma volume and replace that plasma with albumin, which is the main oncotic protein. And when I say oncotic protein, it's responsible for keeping fluid in the vasculature. In addition, albumin tends to be very anti-inflammatory. So all they would do is they're basically diluting off all this bad stuff. And what they noticed were that most of the biomarkers of aging showed they were getting younger. And they also identified 10 proteins that were associated with the aging phenotype and that they were going away the more they got off this.
So this all makes perfect sense to me, but I also know that there's a demand for plasma. People get paid a lot to donate plasma already, and there's demand for blood donation. So I have to think that plasma exchange is going to be something that's culturally controversial because there's going to be some people who can afford to pay for it and some people who can't. And there's going to be some people who are giving their plasma to people who are just using it for anti-aging purposes versus people who have active disease, right?
Now, let me interject there. Yeah, go ahead.
One question. Isn't this sort of similar to what fasting does through apoptosis and sort of the turnover of some of these senescent cells, right? Am I wrong about that?
Well, is it similar? I would say the mechanism is not similar, but the result may be the same. Yeah. Now, but I want to tell you that please don't confuse simply getting rid of plasma with getting young people's plasma, because what they also found in the study is there was a significant benefit getting rid of your plasma, but there wasn't a significant benefit getting young people's plasma.
Oh.
So what we learned is it's not that there's anything special in the young people. It's the fact that you need to get off the bad toxins in the old people.
I see. Okay. That's helpful because I already see this conversation starting to emerge, and I've never heard anyone say that.
That is the key. If you look at the data, the best response was simply getting off the old plasma.
So short of that, this is something that you do in a clinical setting, but for individuals, the questions are, some things that are thrown around is, NAD, glutathione drips, NMN versus NR, vitamin C, vitamin D, and there's a lot of conversation about avoiding seed oils. What do you see are the practical steps that don't necessarily cost a ton of money for people that are the most impactful?
Sure. So the things you talked about, decreasing oxidative stress, glutathione, and I'll comment on something else, and something I'm doing. So there were a couple of studies done at Baylor University, and what they did, of course, we've all noticed that your glutathione stores decrease with age, and glutathione is considered the master or one of the master antioxidants. And so they did some very interesting studies. They were small studies, but they gave very large amounts, 100 milligrams per kilogram of glycine and N-acetylcysteine to elderly people. And now, N-acetylcysteine and glycine are two of the three components that are necessary to form glutathione. And when they did this, these individuals, by every biomarker of aging, got younger. Mitochondrial function improved, senescent cells decreased, there were less gene mutations, cognitive studies were improved, strength training was improved. And so
there's a study with big impact on insulin sensitivity and the combination of those things too, right? Can you touch on that?
Yeah. So, as far as, insulin resistance, of course, we know it's associated with metabolic syndrome, with being overweight, with being obese, but that's also associated with having overwhelming oxidative stress. And so it can work both ways. So decreasing oxidative stress, perhaps giving glutathione, can help with insulin resistance, but also mitigating insulin resistance through appropriate diet and exercise can decrease oxidative stress.
Okay, I see.
Yeah, so it goes both ways. But the really interesting finding was that they were able to significantly reverse all the biomarkers of aging by giving those two precursors to glutathione. So as an individual, you may say, well, why don't I just take glutathione? And the hypothesis from the authors at Baylor was that, well, too much glutathione is no good either. Too much antioxidant is no good. And when you give the two precursors, the glycine and N-acetylcysteine, you allow the cells to make an individual decision. One cell may say, oh, I need glutathione, and take it up and form glutathione. Another cell may say, I don't need more glutathione, but I'll take the cysteine component and make other proteins that I need. So one of the things that I do is I take 100 milligrams per kilogram of glycine and N-acetylcysteine a day. Another thing I do, and I think you and I talked about it, was there was a recent very interesting article on the semi-essential amino acid called taurine. And this publication came out June 8th, 2023, just a little while ago. And taurine is very, very interesting. So many of you out there know that taurine is added to energy drinks. Now, taurine doesn't rev you up like taking guarana or ginseng or caffeine. As a matter of fact, it's a GABA agonist, so it's calming. But taurine has been shown to increase mitochondrial production of ATP, improves electron transport. Now, taurine is stored in the retina, in the brain, primarily the pineal gland, in heart muscle, in skeletal muscle. Most of our taurine, though, we get from eating animal products. Now, we also know that as you age, taurine stores greatly reduce. So by the time you're 65, you typically have about 25% of the stores of taurine as you did when you were 25. So if you were to search the literature, the preclinical literature on taurine and aging, everything is positive. You won't find one negative article on taurine. You'll find that taurine has anti-inflammatory properties, anti-cancer properties, antioxidant properties, and it promotes mitochondrial function. And it has also neurotransmitter properties, specifically being a GABA agonist. So taurine is really very exciting. So in this publication that came out on June 8th, they took mice and monkeys, and they gave them very large amounts of taurine, and it was 1 gram per kilo. And the mice, they got younger. And the mice increased their lifespan up to 15%. the number of mice that went up to 28 months, which is a long time for a mouse to live, increased up to 25%.
Wow.
The monkeys all rejuvenated. So after reading this article on June 8th, the next thing I did was to do a literature search to find the highest dose of taurine that humans have consistently taken. And the highest dose I can find was 10 grams per day. So what I did on June 9th is I got 1,000 milligram capsules of taurine, and I started taking 3 in the morning, 3 in the afternoon, and 4 in the evening. In 5 days, I felt like Superman. My mood was better. My energy was better. I typically start my day at 5 in the morning, and by 5:30, I'm really starting to get fatigued. Well, that fatigue was gone. Went to the gym, I had better energy. This is amazing. Now here's the bad part. At the 3-month period, I started getting diarrhea. And it was clearly related to every time I took my taurine. And, I surmised that my stores are repleted. And so I went back down, which I am now at 6 grams per day. Now, I still feel good at 6 grams a day, but I will be honest and tell you, I felt better at 10 grams, but my gut cannot tolerate that. Now, I have another couple of anecdotal cases. I have a buddy who's 62 years old, and I promise I'm not making this up. After 3 months, he doesn't need his reading glasses anymore.
Wow.
I have another individual that I treated who had a metastatic, very aggressive uterine cancer to adrenal glands. Now, we treated with some combination immunotherapy regimens, and she's 10 years out. She just actually had her 10-year anniversary, I think 3 weeks ago, which is great, but we caused her some issues, specifically some autoimmune issues and progressive fatigue. She's 82 years old. She loves to play tennis, but for the past 2 years, she pretty much sits on the couch, can't get off the couch. Well, I put her on 10 grams of taurine, and I have a wonderful email from her, and actually I saw her in my office last week as well. Her fatigue is gone, and she's playing tennis again.
That is amazing.
So, now I was wondering, why is taurine doing something so amazing? And one of the things I looked at, I'm going to talk about old literature, and that is the thymus and pineal gland. So there was some exciting research really back in the 1990s by Dr. Pierpoli from Italy. And he became fascinated with the involution of the thymus and the calcification of the pineal gland, perhaps having a role in the aging process. So one of the things that he did is he took a young mouse's pineal gland and he transplanted it onto the thymus of an old mouse. And that old mouse became young and increased their lifespan by about 24%.
No kidding.
It was fascinating. It made the cover of the National Academy of Sciences in the United States. Really, really fascinating. So when I was looking at taurine, I wanted to see if it had anything to do with thymus, production of the thymic peptides, and of course T cells and natural killer cells, and I found nothing. And then I looked at the taurine and the pineal gland, and I hit pay dirt. So it turns out that taurine actually stimulates the pineal gland to produce melatonin. Now,
wow.
Some people say, well, why can't I just take melatonin? Won't it do the same thing as the pineal melatonin? And the answer is no. And so I spent a lot of time looking at the literature trying to explain why it's the same molecule. Why can't I take oral melatonin or even IV melatonin and get the same wonderful results as my pineal gland releasing melatonin? Because we do know as we age, the circadian rhythm, the cycling, the production of melatonin when you're 70 from the pineal gland is not like it was when you were 20. And here is the reason. So it turns out it's the location. So right behind the pineal gland, in the third ventricle, there's a recess right back there. And when melatonin is released by the pineal gland, it directly falls and bathes the suprachiasmatic nucleus, which is the biological clock. So it's the location that is important. Now, when we take oral melatonin or even IV, it's barely even crossing the blood-brain barrier. You'll find minimal amounts in the cerebral spinal fluid, and you're not going to find any at the suprachiasmatic nucleus. So we're better off not taking melatonin, but stimulating our own pineal gland to produce what we need.
No kidding. Doc, it's becoming clear to me that we could do this for 8 to 10 hours and never stop and just keep each other going. But the gracious folks at Podpopuli who are allowing us to use their studio are signaling to me that we need to wrap this up. But here's what I propose. I have the ability to do this in a high quality way remotely. Would you be okay with sort of continuing the dialogue over time? We can do it from the office. Okay. And the other thing I have to say is, just to reiterate, I'm grateful for how you've helped my family and for how you've helped me. And I really honestly don't know where I'd be without you. And it's just a soothing salve for me just to be in the same place as you and have this conversation.
Thank you, Thad. You're a wonderful individual, and thank you for sharing that with me. And I'm glad you came into my life as well.
Yeah. Well, thank you. And I love you. And let's do this again.